Okay, so in this session we will continue with chapter number 6. So the title of this chapter is Association Analysis, Basic Concept and Algorithms. So before starting this session, I will ask you some questions to review all the topics covered in face-to-face class. Let's begin with the first question. What's the meaning of association rule? This is an example of an association rule. For example, for this association rule. Yes, diaper implies beer. That means if we buy diaper, we will buy beer. This is an example of an association rule. Yes. After that, can you give me an example of two-item set? Bread milk. Yes, bread milk is a two-item set. Okay. After that, what's the meaning of a frequent item set? So the support of this item set is more than a threshold, not less than, but more. To say that our item set is a frequent, the support of this item set must be more than a threshold. And this threshold is the support min. How we can calculate the support of an item set? 60%, this is an example. We can find another support. It depends of the application. So how we can calculate the support of an item set? Number of appear divided by number of item. Number of appear not divided by number of item, but divided by number of transactions. Yes. So the support of an item set equal the number of transactions that contains this item set divided by the total number of transactions. Very good. After that, if we have a rule X implies Y, what is the support of this rule? Support of R. X divided by Y. Support of R. No. Only the support of R. Equal the support of X and Y, not divided, and Y. For example, if we have R, milk, bread, imply beer, this is X and this is Y. So support of R equal support of milk, bread and beer together. So we will count the number of transactions that contain milk, bread and beer, and we will divide by the number of all transactions. It is clear? This is the support of a rule. After that, yes, it's okay for recording. Yes, in progress. It is clear for the support of a rule R. Good. Let's move to confidence. What is the confidence of a rule R? Equal the support of xy divided by support of x. So this is the support of our rule is equivalent. The support of x and y, or support of our rule, is equivalent. So we divide the support of our rule by the support of x. For example, here for our rule, the support, the confidence of our rule equal the support of milk, bread, beer divided by the support of milk and bread. Any questions? It is clear? Okay. Let's move now to a priori principle. Can you explain me what's this principle? What's the meaning of a priori principle? What does mean a priori principle? Test for frequent item. This is not the a priori principle. The a priori principle means when an item not meet threshold, all the descendant, yes. So, for a priori principle. The a priori principle say that if an item set is frequent, then all its subsets must also be frequent. This is a priori principle. And why we use the a priori principle? Why we use the a priori principle? To reduce candidate. Very good. To reduce candidate. So here, if A, B is not frequent, is infrequent, so all the superset will be pruned. All the superset of AB will be pruned. Yes. To reduce the number of candidates. Very good. So to reduce the number of candidates, we use pruning techniques. So a priori principle is one of the possible pruning techniques that can be used to reduce the number of candidates. We can also reduce the number of transactions, and we can also reduce the number of comparisons. So let's see together how we can reduce the number of comparisons. Candidate counting. So scan the database of transactions to determine the support of each candidate item set. So to reduce the number of comparisons, we can store the candidate in hash structure. So hash structure is used to reduce the number of comparisons. So we reduce the number of candidates by a priori principle, and we can use hash structure to reduce the number of comparisons. So instead of matching each transaction against every candidate, we will match it against candidates contained in the hashed buckets. Have you an idea about hash structure? Okay, let's suppose we have 15 candidate item set of length 3. For example, here one of this candidate of this 3 item sets, 1, 4, 5, 1, 2, 4, 4, 5, 7. So 1 here is an item, 4 is another item, 5 is another item. In our example, items are numbers, are represented by numbers. For example, milk by 1, bread by 4, etc. So to generate hash tree, you need hash function and a max list size, max number of items sets stored in a list node. So if number of candidate item set exceeds max list size, we will split the node. So this is the hash tree that corresponds to this 3 item sets. So our hash function is x modulo 3, the rest of the division. So we will find in the left 147 in the middle 258, and in the right 369. It is clear for the hash function here, y1 and 4 and 7 together, because 1 mod 3 equal 1, 4 mod 3 equal 1, 7 mod 3 equal 1. And 2, 5, 8 together, because 2 mod 3 equal 2, 5 mod 3 equal 2, and 8 equal 8 mod 3 equal 2. It is clear? 7 mod 3 equal 1, because 7 mod 3, the rest of 7 mod 3 equal 1. So let's 7 we will divide by 3 equal 2, and the rest equal 1. This is 7 mod 3. It is clear? So after that we will begin with, for example, here 1, 4, 5. So this is our 3. We write 1, 4, 5 here, because 1 give us in the left. After that 1, 2, 4 here. Yes. After that 5, 4, 7 here also. So I will prepare a new page. So this is the first step of constructing this hash table. So my function is 147 to 58, and here 369. So 147 will be here. Sorry, 145, because here I begin with 145. Okay, it is clear. After that 124. This 124. Also here 124. After that 457 in the same place, because 4 is 457. After that 125. Yes, in some group. 125. 125. So the number is more than 3. There is a max list size. The number is more than 3. In our example, more than 3. The number is more than 3. For this reason, I will split this content into 3 parts. I will obtain here 145 here. 124 here, because 2, this is 2. 457 here, the second part, and 125 here. And I will, will be deleted, etc. So in the final, I will obtain this hash tree. So then this is not very important how we can construct this hash tree, but the important is to keep in the mind that hash tree is used to reduce the number of comparison. So this is my hash tree. After that, the association rule discovery using hash tree. Hash on 147, the comparison will be with 145, 124, 457, 125, 458, 159, and 345. It is clear? After that, if I will hash in 258, the comparison will be 124, 457, 125, 458, 159, etc. Yes, for you, let's suppose that we have the hash tree. After that, how we can compare or how we can reduce the number of comparisons using this hash tree. And for if we will, so let's suppose that this is our hash tree. If we will hash on 147, I will use only this part and this part of the tree. It is clear? Only the candidates on 145, 124, etc. If I will hash on 258, so the comparison will be on this part, this one, and this one. And if the comparison will be on 369, the comparison I will use this part, and this part. Yes, I will explain how the comparison, we can perform this comparison via an example. This is my example. Let's suppose that I have a transaction like this. 1, 2, 3, 5, 6. So the question in this example is, what are the possible subsets of size 3? Okay. Type. Your attention please. For this part, المهم هو الexample. يعني إذا ما فهمتوا شيء في الإكزامبل قولوا لي إيش مو مفهوم وأنا أعيد من أول وجديد. هتفهموا الهاش تري كيف بنستعملها عن طريق الإكزامبل. أوكي؟ So for this slide, let's suppose that we have this transaction T. So in this transaction, how many items we have? 5, not 6, 5. Only 5. 1, 2, 3, not 4, 5, 6. So 5. So we want to extract all the possible subsets of size 3. All the possible subsets of size 3. So to extract it, there are some levels. So for level number 1, I will get the first item 1 in my example here, and after that the rest. Here 1 in red, the rest is 2, 3, 5, 6. It is clear for this first step. Okay. After that, for the second, I begin with 2. So I keep 2 in red, and the rest will be 3, 5, 6. Because we will use it after that with 1 in the box, because after that we will make combination with 1, 1, 2, 1, 3, etc. To say that this is the rest. 3, 5, 6 is the rest. So we put it in the box to say that it is the rest. From 2, the rest will be 3, 5, 6. After that, from 3, here, the rest will be 5 and 6. It is clear, the first level. After that, in the second level, here, why we don't use 5 in the first level, 5? Here, why we don't use 5 and the rest 6 in the box? Do you hear me? Yes, because the size is 3. So the last one will be 3, 5, 6. Okay, so from level 1 to level 2 now, we will add here, from 1, we get 1, and we will add 2, and the rest in the box. After that, we will get 1 and 3, and the rest in the box. After that, we will get 1 and 5, and the rest in the box. It is clear? Okay. After that, from level 2, we will get to level 3 to obtain subsets of 3 items. So the first one gives us 1, 2, 3, 1, 2, 5, 1, 2, 6. It is clear? After that, the second one, 1, 3, 5, 1, 3, 6, 1, 5, 6, etc. So this is the manner to extract subsets from a transaction. Here in our example, the subsets are the size of this subsets equal 3. So if the size of this subsets equal 2, for example, in this case we have to add another level. So now we will use the hash tree to reduce the number of comparison. Okay, so this is our hash tree with 147 in the left, 258 in the middle and 369 in the right. Okay, so we begin with our transaction here in the root. Our transaction is in the root. 1, 2, 3, 5, 6. After that, we will make here 1 plus the first. Yes, of course. Yes. So here in our example, in this transaction, we will keep 1. So 1 will be in the left here. 1 plus the rest. Okay. After that, 2. The 2 will be in the middle. The 2 here in the middle. 2 plus the rest. And the 3 in the right. Three plus the rest. 3 will be here. It is clear, this first step? Yes. The same example, yes, of course. But here we will use the hash tree, and we will see how we can reduce the number of comparison using this hash tree. After that, this transaction I will add 1, 2 plus the rest, 1, 3 plus the rest, and 1, 5 plus the rest. So 1, 5 and 1, 2 will be in the middle, and 1, 3 will be in the right. It is clear? No, it is not clear. So here we have 1 plus, 2 plus, 3 plus. It is clear in this level. This level is clear for you, Ahmad? After that, we will make the same with 1. Yes? Here. Do you see my pointer? The blue one here. Okay. So I have this transaction. 1 plus 2, 3, 4, 5, 6 here. Do you see this transaction? After that, when I will move in the tree, in this node, I will make the next level. So the next level here, the next level will be 1 plus 2 together and the rest, 1 plus 3 together and the rest, and 1 plus 5 together and the rest. It is clear? So 1 plus 2, that's 1. 1 plus 2 will be in the middle, here. 1 plus 3, we have 3, will be in the right, here. Okay? 1 plus 5 will be in the middle, here. Why? Because here we have 2 in the middle, we have 3 in the right, we have 5 in the middle. It is clear now? It is clear? Okay. So you can't forget the yellow box. So the yellow box represents this hash tree. This one, our hash tree. This is the yellow box. For you, you can't forget this yellow box. Just use this box. 1, 2, 3. So 1 here, 2 in the middle, 3 in the right. After that, عندما ننزل حنشوف ولا نستعمل النمبر الموالي. هنا النمبر الموالي هو 2 في الوسط. هنا 3 حيكون على اليمين. 5 حتكون في الوسط. واضح؟ بعدين هنستعمل في الكومباريزن بالطريقة هذه إلا الأعداد أو ال 3 items الموجودين هنا. هنستعمل ال 3 items الموجودين هنا. 3 items هذم مع هذم مع هذم مع هذم مع هذم. يعني هنا في الكومباريزن ما بنحتاج ان نعمل comparison with all possible 3 items. هنحتاج الا 3 items الموجودين هنا وهنا وهنا وهنا. يعني الا في الازرق هنحتاج 11. بس في الشيء العادي لازم نعمل 15. اللي في الميدل ما عندها كيف تنزل. هنا هذه بتتحدث على هذه. ما في نود هنا، ما بنقدر ان ننزل اكثر. عاصم هنا بتتحدث على الترانزاكشن هذه. ما في node like this. ما في node عشان ننزل like this. So in this example, we can see how hash tree can reduce the number of comparison. يعني هنا نحتاج comparison against only 11 out of 15 candidates. 11 out of 15 candidates. Any questions? So what are the factors affecting complexity? The choice of minimum support threshold. So lowering support threshold results in more frequent item set. If we have the minimum support threshold is not very large, in this case we will find more frequent item set. This may increase number of candidates and max length of frequent item set. Also, another factor affecting the complexity of extraction of rules is the dimensionality of the data, the number of items. More space is needed to store support count of each item. And if the number of frequent items also increases, both competition and input-output costs may also increase. The third factor that affects the complexity is the size of the database. Since a priori makes multiple passes, runtime of algorithms may increase with the number of transactions. And the fourth factor that affects the complexity is the average transaction width. So transaction width increases with denser data sets, and this may increase max length of frequent item sets and traversals of hash tree. So keep in mind that there are 4 factors affecting complexity: choice of minimum support threshold, the dimensionality of the data set, the size of the database, and the average transaction width. Any questions? Are you here? Let's move now to maximal frequent item set. So what's the meaning of an item set, a maximal frequent item set? An item set is maximal frequent if none of its immediate supersets is frequent. So in this example, here AB is infrequent, ABC is infrequent. So in the gray color are infrequent. So why AD is a maximal frequent item set? Why AD is a maximal frequent item set in this example? So what are the superset of AD? Now, superset. So the subset of AD are ABD, ACD. Yes. So AD is a set. To move to a superset, we add. So ADC, for example, is a superset of AD. I talk about AD, this one. My question is, why AD is maximal frequent? So AD is maximal frequent because its immediate superset are frequent. None of its immediate superset is frequent. So in our example, the immediate superset of AD are ABD and ACD. ABD is infrequent, ACD is infrequent. For this reason, we say that AD is maximal frequent. It is clear what's the meaning of maximal frequent? Another example. This one also is a maximal frequent, ACE. Why? Because the superset of ACE, the immediate superset, are infrequent. Any questions about maximal frequent? It is clear? Okay. Let's move to closed item sets. An item set is closed if none of its immediate superset has the same support as the item set. To say that closed item set, none of immediate superset has the same support as the item set. For example here, yes, for example, B here, what are the immediate superset of B? The immediate superset is AB is the first one, after that the BC, the BD, yes. So this is the support of B. 5. 5 is different than 4, then 3, and then 4. And this reason we say that B is a closed item set. It is clear? But for you it's clear that the closed item set? So this is another example, and we can find in this example closed but not maximal. We can find closed but not maximal item set. We can find closed and maximal item set. So when we have a frequent item set, or sorry, when we have maximal frequent item set, we can say that this item set is closed. We can also say that this item set is frequent. It is clear? And when we find a closed item set, a closed one, we can say that this item set is also frequent item set. Let's move quickly project database. So we can make projection of a database, projected database for node A. For example, the AB will be B, because here we have A. The BCD will be empty, because we don't find A. The CD will be CDE, because we can find A, etc. It is clear, projected database, how we can make project database for a node A, for example, in our example. Another example is ECLAT. So for each item we store a list of transaction ID. For example, here for A, this is the list of transaction that contains A. This is the list of transaction that contains B. This is the list of transactions that contains C. It is clear, ECLAT here. So if we want to determine a support of any K item set, we can make intersection between the TID list of the 2K-1 subset. For example, here in our example, we want to calculate the support of AB. So we use the list of A, we make intersection with the list of B. This is the intersection, so the support will be 1, 2, 3, 4. The support will be 4. It is clear? Okay. Just I want to save the attendance.